This is a modified talk that I just gave at Perimiter Insitute for 100 years of quantum, which includes a couple of observations that came out of the discussions. The biggest change is the title, which makes the underlying claim more prominent. The quantum principle, that is what quantum mechanics is all about, is simply the lower bound on the entropy, the third law of thermodynamics, or that no information can be acquired below a certain threshold, or that we cannot prepare a system perfectly, or that there is always a minimum interaction with the environment. These are all similar statements in the sense that one implies the other. This to me is a very important insight and result, and so I'm kind of repeating myself if you've seen other talks about our research program. But I've also seen that other people had to repeat the same thing for 20 years before others noticed, so there is that. Let's get started. If you open a textbook in quantum mechanics, you're probably going to be told this story, that we had the classical mechanics, but classical mechanics had some problems. It didn't predict the correct black body radiation spectrum, it did not predict at all the photoelectric effect, and it predicted that atoms would be unstable, that electron would fall on the nucleus. And so what happens is that people started futzing around with matrices and waves in find something new that has some kind of correspondence with classical mechanics, and then we get quantum mechanics. That's basically the story that we tell, which is kind of what happens historically, but in physics textbook you kind of have stories instead of histories. So what is the problem with this story? Is that it fails to tell us what is the ultimate reason as to why classical mechanics fail. And therefore it doesn't even tell us what is it that quantum mechanics is fixing. Now, a lot of people that work on foundations are more interested to explain quantum mechanics and why quantum mechanics work, and I guess because I have a background in engineering and engineers like to study failures, I actually am much more interested in understanding what is it wrong with classical mechanics and what is it that it's doing incorrectly, and that might give us some insight as to what actually is quantum mechanics fixing and why it works. So, since a lot of the classical failures are related to thermodynamics, and there is this idea of uncertainty in quantum mechanics, let's look at the relationship between entropy and uncertainty in classical mechanics. So we're actually going to look at classical mechanics. So what we want to do is to plot entropy against uncertainty. And one of the things, the formula that we're going to use for entropy is the Gibbs entropy, which is minus rho log rho. But here's the problem. Typically, we just say logarithm of rho, which technically is incorrect because rho is a probability density, and therefore it's not a pure number, and we shouldn't take logarithm of things that are not pure number. So we multiply this rho with a constant h that we call h for no apparent reason. And this constant actually has a physical meaning. If we had a uniform distribution rho over a volume of h, of an area of phase space h, then rho would be 1 over h. We would have h that simplifies with h, so that we would have logarithm of 1, and logarithm of 1 is 0. Therefore, this h tells us the area of a uniform distribution that corresponds to 0 entropy. So it fixes the 0 for the entropy, this constant h. Okay, so that's the formula that we're going to use to plot uncertainty against entropy, and this is the plot that you get. The reason that you get this plot is that the Gaussian maximizes the entropy for a given uncertainty. So if you fix the uncertainty, the sigma q times a sigma p, and you can go increase up and go up in entropy until you hit the Gaussian, because the Gaussian is going to give you the highest entropy with a given uncertainty. And so you have that the entropy of any distribution is less or equal to the entropy of the Gaussian with the same uncertainty, which is logarithm of 2 pi e sigma q sigma p over h. And again, see how h essentially solves the unit. This would be units of phase space, and this is now a unit of phase space. Okay, so if you look at this expression, should kind of feels familiar, because what we do is move things on the other side and exponentiate, and what we have is sigma q sigma p is greater or equal to h over 2 pi e, the exponential of the entropy. And since we have an h over 2 pi, we can call this h bar, and so we have h bar over e, the exponential of the entropy. Again, we don't know that this h bar has nothing to do with quantum mechanics. The only thing that we know is it's the constant that fixes the zero of the entropy. And so what we find is that the entropy puts a lower bound on the uncertainty. If we have a certain entropy for a given distribution, its uncertainty cannot be greater than this. And by the way, this quantity, the exponential of the entropy, is also known as the entropic volume, and there is a paper by Michael Hall that shows that if you have a probability distribution and you want to characterize some type of volumes for that distribution, probability distribution that has certain properties that that volumes might have, you actually have to get the exponential of the entropy. So again, this Gibbs entropy, the Shannon entropy, and the von Neumann entropy are very particular because they actually give you a notion of measure that actually works as you would expect. Okay, so we have this nice result, and this is kind of looks like an uncertainty principle, except that this is not a universal quantity. This quantity depends on the entropy that you are going to measure for each specific distribution. But if we had a universal lower bound to the entropy, then we would have a lower bound to this, and then we really would have an uncertainty principle. So the question is there a universal bound, a universal lower bound to the entropy? And if you think about, not in classical mechanics, but in thermodynamics, we have something called the third law, which tells us that the lowest the entropy can be is 0. So all this region then is excluded by the third law of thermodynamics. There are no distribution that can be here. The other distribution up here are excluded by the Gaussian boundary. So this is the only region where we can have probability distributions, so we can have ensembles. And you see now that there is a minimum for the uncertainty here. Since s has to be greater or equal to 0, the exponential of 0 is 1, we must have the sigma p is greater or equal to h bar over e. And this is what I call the classical uncertainty principle. So now we can, compare the two theories. We have the classical mechanics plus the third law. It tells us that sigma p has to be greater or equal to h bar over e, while in quantum mechanics we have the sigma p has to be greater or equal to h bar over 2. Note that in quantum mechanics, the entropy is already non-negative, so we don't have to exclude anything. In a sense, quantum mechanics incorporates the third law. Quantum mechanics takes the third law very seriously, while in quantum mechanics is kind of optional. But the other thing that you can see is that this blue line is the classical Gaussian bound, and this red line is the quantum Gaussian bound. And you see that even for just a few units of uncertainty, they become very, very similar to each other, right? So again, in principle, these are two theories and they both have a constant, and then you go and find the constant experimentally, and you find that since that high region, this function have to correspond both to experimental evidence and they have to essentially be the same, then you find that the constant, strikingly, has to be the same in both classical and quantum mechanics. So the only behavior, the difference in the behavior is actually not the constant, but is the behavior at low uncertainty, at low entropy, right? That's where the theories are different. And so if you look at this, then you start thinking, well, is this the only thing that makes it different? Is really the only difference between classical mechanics and quantum mechanics is that quantum mechanics actually is serious about the third law, and classical mechanics is sort of takes it as an option. Well, one way to study this further is through this conjecture that I had for a long time. Since we see that these plots become very similar to each other at high entropy, then the question becomes whether does quantum mechanics recover classical mechanics at high entropy. Since these two theories becomes ideally, right, they become very similar at high entropy. It doesn't matter whether you use quantum mechanics or classical mechanics. You're going to make some mistake using classical mechanics, but then again, if all the quantum effects sort of disappear at high entropy, then there is no problem. We can just use classical mechanics. So I had this conjecture for a long time, and I always tried, when I was in conference and so on, to find people that maybe would help me develop this conjecture and prove this conjecture one way or the other. And after a few years, I got frustrated. And so what I did, since I have a presence on YouTube, I actually just posted a video on YouTube with the conjecture. And then what happened, that an experimental atomic physicist replied to me with some idea, and after a few months we actually had a paper which we are still trying to find the correct journal to publish it in, but the result is basically there. So this is one of the reasons why I think that we have to do this sort of more open type of research, because I really think that all the insights that we have to fix the foundation of physics are already there. They're just sprinkled around in different fields and in different heads, so we just need to make a synthesis of it. So anyway, what can we do with this limit? Well, there are a couple of things that you can do. The first thing that you can do that is very neat is just reinterpret all results. So, for example, we talked about the black body radiation in classical mechanics and quantum mechanics being different, and the typical thing that you see in textbook is that this is the black body radiation for a quantum in the quantum case, and if you take an expansion of this into a small frequency, then you see that the leading term is actually the classical term. So you recover classical mechanics for low frequencies. Well, one of the things that you can say is that if we are at thermal equilibrium, then high entropy is equivalent to high temperature, and high temperature is equivalent to low beta. So instead of taking the expansion in terms of frequency, we can take the expansion in terms of beta, and lo and behold, the first term is the same. So we can recover the classical blackbody radiation at small beta instead of at small frequency. So the limit is more in line to what we say. It's at a high entropy that you get the limit. Or, for example, this is a paper from Wigner, like a very old paper from 1932, where he takes the Wigner function of a thermal state and shows that the classical distribution is the leading term of the expansion in h bar. And again, what does it mean to expand in h bar? Since it's a constant, it doesn't really make so much sense, but the thing that we can say is that, again, at thermal equilibrium, high entropy means high temperature, and high temperature means low beta, because beta is just the inverse of the temperature. And so what you do is you can recover the same limit with a more meaningful expansion in beta. So if you do the expansion in beta, you get this, and this is essentially the same term that you would get if you did the expansion in terms of h bar. So again, I can't go and reinterpret all the results that have been done in the past 100 years, but the point is that you can get physical meaningful expressions that are consistent to what we claim. Of course, that's not enough. We actually have to recover the classical limit more in general. And what does it mean? How do we do it? Well, let's go back to this graph. What we're looking for is a map that acts on the ensembles that increases entropy of all the mixed states of quantum mechanics, such that every level set of entropy is mapped to another level set. So if we take any point on here, any mixed state on here, we are going to increase in entropy, so we're going to get a mixed state here. And what we want is that if there is if two elements are connected through a unitary map here, and we see how the unitary map act after the entropy increasing map, well, we want still that map to be a unitary map. So in a sense, we want it's not really a commutation between this and the other, but it's sort of the transformed of the unitary through this entropy increases map is still a unitary. And if you want to have this property, what needs to happen is that the commutator between x and p essentially gets to be modified only by a constant. Because if it were not modified by a constant, then you would find regions of phase space that are sort of transformed differently, and then you would be able to transform the entropy differently for different mixed states. So if you want such that everything sort of increases entropy, you have to do this type of thing uniformly, and that is going to mean that that the commutator only changes up to a constant. So you can see this very, very nicely in classical mechanics. If you have an entropy increases map that has to be increasing by a constant, well, this increase in the entropy is going to be the logarithm of the Jacobian. And if the Jacobian is constant, then that's exactly when you're going to have that all the entropies are going to increase the same. And so if the Jacobian is a constant, then it also means that the Poisson bracket is sort of rescaled by that constant, and you can do the argument in the other way as well. So in classical mechanics, it's very easy to go back and forth. In quantum mechanics, is a little bit more difficult, because if we have, for example, something that stretches both x and p by this factor of square root of gamma, we know that this is going to be a stretching map in the sense that the commutator is going to be rescaled by a gamma, but this is not enough to define the full map because of operator ordering. So we not only we have to define how x and p change, but any polynomial of x and p, because they might be different. So fortunately, it's not even so difficult to actually find the solution. What needs to happen, since we have a transformation that has to increase the entropy, then this has to be an open quantum system, because unitary evolution have to keep the entropy the same. So you have basically a quantum channel, a CPT map, whatever, and you can imagine this to be continuously stretching this phase space continuously, and then what it means is that this transformation has to be described by the Lindblad equation, which is the equation for open quantum system. So all that we need to do to fix this equation is to find the correct L and the correct gamma to put there to get the right behavior that we want. And it turns out that the L is actually something very simple, is the antiladder operation. It's A dagger, the combination of linear combination of x and p, and that the gamma here is actually just a lambda. So what happens is that there is an ordering that is preferred, right, which is the, if you know what it is, it's the antinormal ordering, and therefore the Hosimi Q representation is the one that is preferred. The Wigner function works with sort of the completely symmetric ordering, where you take all the permutation of x and p so that you get the correct ordering, and instead the Hosimi Q is developed in terms of the expectation are what you get from the antinormal ordering. So what happens is that the Hosimi Q is simply stretched. So if you have your pseudo probability distribution in terms of this alpha and alpha dagger, you were going to see that in Hosimi Q you're just stretching this distribution. In a Wigner function, which is in terms of position of momentum, is your probability distribution, pseudo probability distribution in position of momentum. This also gets stretched, but then it gets convolved with a Gaussian, which essentially makes it that the zone with negative probability remains small. And then what you find is that in the limit, the Wigner function is going to stretch and become essentially very similar and will coincide with the Hosimi Q in the limit. And this makes sense because it's basically telling us that since the Hosimi Q and the Wigner function starts to be similar to each other, the ordering of the operator is also not going to matter, and you're going to get the same expectation regardless of what the ordering of the position of momentum, which basically means that for this state, it's kind of like position of momentum commute when you go and get the expectation value, which is what you want to have to basically show that you have a classical behavior. So this all makes a lot of sense, but there is yet a third way to look at this, which is nice, because what we want to do in our approach in the assumptions of physics is we want to have as many ways of looking at the same result to sort of build intuition in different ways. So we can recover the way that the mathematicians do the limit by making it make h bar goes to 0, which of course physically makes no sense because h bar is a constant, but we can see now, we can give an interpretation of what actually is going on. So The idea is that in the physical limit we start with a commutator with x and p, and then we make the map, and then the commutator gets rescaled by the factor lambda. Now what we can do instead is redefine the original space. So we take the original space, we divide the commutator by lambda such that after the map we have the standard commutator, right? And this essentially, the intuition is that instead of taking the states and going up to infinity, what we do is we rescale the zero of the entropy of the pure state and bring it down, right? So instead of going up in entropy for the states, we're moving down the reference of the pure states to minus infinite entropy. And what you can see here is that since we have this IH bar over lambda and we're making lambda goes to infinity, this side is going to 0. Which is kind of like saying that on this side we're taking h bar goes to 0, right? So this is what the limit is doing. It's a little bit better here because now h bar is constant. It's this lambda that's going to infinity, so this ratio is going to be 0. But mathematically, it's basically the same. We're taking our Lie algebra of the commutator and make what's called a group contraction by taking this h bar and make it go to 0. And of course, that's exactly the limit of how mathematicians do that. So this is completely consistent now to what we already know. So every time that you see a limit h bar goes to 0, you can say, yeah, it's not really h bar goes to 0. We're just taking the pure states, putting it at minus infinite entropy, which means we're taking the limit of high entropy. So now, what is nice about this is that the limit of the non-relativistic limit is exactly formally the same as what we have for the classical limit for quantum mechanics. So if we have a relativistic system, right, that's the correct one, but if we are at low speed, then we can approximate things with non-relativistic mechanics. And of course, mathematicians also define this limit by saying that c goes to infinity, which of course physically does not make any sense. But if you're just looking at the mathematical structure of all the groups and so on, you can do that and it's the same thing. Similarly, if you are at low entropy, you have to use quantum mechanics, but if you go at high entropy, then your quantum effects are going to be essentially more and more masked by the uncertainty that the high entropy gives you. At some point, you're going to be able to say, okay, I'll just use classical mechanics as an approximation and it's going to be fine. And of course, again, mathematician might say, okay, well, I take this limit by using h bar that goes to 0, which again is not physically meaningful, but again, if you're just interested in understanding what happens to the group structure, you can take that limit mathematically and it's perfectly fine. So now we basically have essentially the same thing that happened in both cases, and in both cases there is no mechanism, right? So a lot of the time people that look for a mechanism to get to classical mechanics, but if you think about it, that's not how we think about the non-relativistic limit. We just say, if we are at low speeds, then you get non-relativistic mechanics, but the mechanism for which, nobody asks which is the mechanism for which the speeds are low. Like if we have a spaceship, nobody tells us, oh, but what is it breaking? Well, what is making our spaceship slow? Like, is there something that... No, it doesn't really matter. The mechanism doesn't matter. As long as you are at low speed, you can use non-relativistic mechanics. And so the same thing is going to happen for the classical limit. We have to be a high entropy. Why are we at high entropy? Is it because the environment is interacting with our system and there is entropy production that is being put in our system? Or is it because our preparation device or measurement devices are so bad that our preparations are really messy and so they're at high entropy? It really doesn't matter. In either case, we're going to be able to look at a higher entropy description. That's the only thing that we can do. And therefore, classical mechanics is going to result in a good approximation. The other thing that we can do is also, again, reinterpret something that we typically do in quantum mechanics, which is the Dirac's correspondence. So to quantize a classical theory, you take something that has Poisson bracket and you replace the Poisson bracket with these commutators, right? Why are we doing that? What does that mean? Well, what that means is basically you're asking for a theory with an entropic lower bound that recovers the classical one at high entropy, because if I now make the limit for h bar that goes to 0 at high entropy, I'm going to recover the Poisson bracket. And what is interesting to me is that the math tells us that there is only one way to do it, because the Moyal bracket is the unique one-parameter Lie algebraic deformation of the Poisson bracket up to isomorphism, so the commutator would be one such isomorphism. So if you're asking for a classical theory that actually has a strict lower bound on the entropy, then there's only one way to do it, and you find quantum mechanics. So really, quantizing a classical theory means putting a lower bound on the entropy. So really, what quantum mechanics doing, the quantum principle, how we recover quantum mechanics, is basically realizing that, look, from a thermodynamics perspective, from an information theory perspective, from lots of different perspectives, we have to put a lower bound on the entropy, because there is always going to be uncertainty in our preparation, not our measurement, our preparation, which is more important. There is always going to be some interaction with an environment which we're going to have to be at equilibrium to make sense of what the systems that we are defining and make sure that things make sense. So there is always going to be some type of a variability that it's going to be in our ensemble. So we need to put a lower bound on that, and lo and behold, the only way to do it is through quantum mechanics. So one of the comments that I got when I was presenting this perimeter, well, why can't we simply keep classical mechanics with a lower entropy? As I said before, we can take all the classical distribution and then you say, okay, below this distribution, below this zero entropy, we're just gonna throw them out. And so we're just gonna have the set of all ensembles, the set of all probability distribution for which the entropy is greater or equal to 0. And we say, oh, those are our states, right? All our distribution are like that, are our states. So why can't we just do that? Why do we need quantum mechanics? And the problem is that if you only do this, if you just take classical mechanics and put this lower bound excluding over else, what you're doing is something that it's in some sense physically inconsistent. The math is still consistent. Mathematically, everything works fine, but you're actually in the math, you're saying two things that when you go and interpret the theory, they're actually in contradiction to the other. So on one hand, you're basically saying ensembles with lower entropy do not exist. There is a lower bound, and the information below a certain threshold is not accessible, right? Because you removed all the distribution that are finer than the one that you can get with zero entropy. But then on the other hand, you can define probability on an arbitrary small region. So if I have a region U, right, as small as I want, I'm going to be able to see what is the probability density there, make their integral, and calculate a probability. And this probability corresponds for me measuring something at U. So I'm defining what happens in this measurement of U, so I'm positing that these things make sense, these things that exist. But if I were able to measure something here, then of course I would be able to take more information than what I said that I can't, right? So on one side, I'm basically saying that the information below a threshold is not accessible, but on the other side, I'm saying that there is no minimum threshold for a combined measurement of position and momentum. And this is the problem, because if there is no minimum threshold, then I can go and violate the lower bound on the entropy. And this also tells you why this idea of a lower bound on the entropy necessitate measurements that are incompatible with each other. That if I measure position, then I can't measure momentum, and vice versa, because if I'm able to measure both of them at the same time, being that they're continuous quantities, at some point I get a region that sort of violates the lower entropy bound. So I hope this makes sense and sort of starts telling you why quantum mechanics has to be different. In mathematical term, we can't simply use the Borel algebra of the product of position and momentum, and that's kind of why we have this quantum logic, which is not really a logic, but it's the set of statements upon which you can put a probability, and those are going to be that set of statements, the lattice of statements is going to be different in classical mechanics and in a theory like quantum mechanics, where you were putting a lower bound on the entropy. So to conclude, this is what I hope what's going to happen in 100 years is that we are going to have an introduction to quantum mechanics that basically tells us that classical statistical mechanics is incompatible with the third law. And it would be nice to reinterpret all the results that are problematic as coming directly from the third law. And stability of atoms is very easy, because if the atoms collapse at some point, it's going to violate this the lower bound of the entropy. The photoelectric effect, I have no idea why it would come to that. But again, if all that we said is correct, then there has to be a reason. And then the idea should be that in 100 years, you're going to be able to say, okay, let's develop a theory that puts a lower bound on the entropy and recovers classical mechanics at high entropy. And then with some very simple mathematical framework, you're going to be able to recover quantum mechanics. Now, unfortunately, we are missing the technical tools to be able to make such simple derivation, and also to make all that we said a lot more mathematically rigorous. Unfortunately, we don't have currently the correct base theory to be able to show in a much more mathematical precise way that the assumption or lower bound of the entropy is equivalent to the assumption of taking quantum theory. And the problem is that we don't have a correct base theory to be able to do this. So what I mean by base theory is that in set theory, for example, you go and prove that the axiom of choice is equivalent, for example, to Zorn's lemma. And how you do it is that you have a more basic theory, which is the Zermelo-Frankel set theory set of axioms. And then you show that this set of axioms is independent from the axiom of choice, and then you can presuppose the axiom of choice and show that you can prove the Zorn lemma, or then take the Zorn lemma and prove that you can get the axiom of choice. So that way you can prove that these two things are equivalent under this base theory. And I am missing the base theory. I don't know what is the set of axioms that I have to hold for any reasonable physical theory, and then add on top the assumption of classical mechanics or the assumption of quantum mechanics, and show that these things are equivalent. And that's kind of what our research program on the assumption of physics is all about, is finding this base theory. And it's gonna take some time, and that's why I'm also on YouTube, to raise awareness that this is the correct way that we should do it to tackle these questions as the foundation of physics. So if you're interested in this type of research, we have a website. I have another, on this channel, I show some of the results. I have another channel where I try to make some of the more of the research discussion happen. So if you're interested to learn more about the research, you can subscribe. You can look at our website. If you're interested in making sure that research actually happen, you can give us a contribution. And if you have some technical expertise that might help us make progress, do reach out. Thank you again for your attention, and see you next time.